He's made it.
Don't push me. Not cool, meds. Don't do it again.
Amelia.
Oh, he just.
Alan made it. Jaden made it.
Okay.
So I have COVID, so
Okay. You'll need to make up another quiz next week too. So use this time to get caught up.
okay. Did we do any other worksheets or anything?
Yeah, you're gonna need to watch the whole class recording and see what you get. I can't sum it up. I can't sum the whole class up to you in 10 seconds. So. All right, guys. You need to make sure that you turned in 90, 91, and 92. This will be your last chance for full credit. If you didn't turn it in Google Classroom, you can still turn it in hard copy. But before we get started, and you need to put your phones and smartwatches up to the side of the room before I get you your quiz. Our quiz is no calculator.
Not a free rule that he recommends us to memorize. No. N of 0. And probably that's what that ends up.
Right, the denominator.
Make N of 0. Number, then put 0. Next to
Right, that's equals 1.
yeah.
And 0
We also put infinity into infinity.
7, you can look up what you need, and I think that should be in that file over there. I do have some handouts for you guys after the quiz today. I didn't put them out for you to grab on the way in, just because I know they're kind of in your way while you're quizzing. So when you turn your quiz in and you go pick your phone back up, please grab one of each of the handouts before you go sit back down. As I mentioned last class was a little bit, we didn't have much to go over, but today you've got the quiz and we'll need to go over our 3.2 stuff. So as soon as the quizzes are all in, I'll let you know and we will move that direction.
Okay. Let's talk about that. So this one, determine the initial quantity if we plug in 0 for t. How are we supposed to solve that with a calculator?
I'll tell you that. Same way you should have done on the worksheets.
Okay.
I've got all the quizzes in. So again, when you picked up your phone, I'd ask you guys to pick up all those handouts on the front table. Looks like a lot, but we'll be able to look at all of that, even with just the class time we have left. But if you forgot to pick those up, then please go and get them. So the next set of information can be a lot. It just kind of depends on how much of it you remember from Algebra 2. But it is a quicker turnaround time. We'll be able to go through all of the notes and some practice and have you practice the very last one, number 97. That one you might need to spend an extra 5 or 10 minutes outside of class. And then next time I see you, today is Thursday and it's an A week, so I don't see you again until Tuesday. But on Tuesday, I can give you the first half of class of time to look that stuff over and ask any clarifying questions you need to ask, and then we have to take that quiz the second half of next class. So again, a little quicker turnaround time, which I tried to give you guys a little heads up on last time, just because last class was a little bit lighter. Okay, so 1.9 was about inverse functions. 3.1 that you just quizzed over was on exponential functions. And 3.2 starts the logarithm process. So we do a little bit of logarithms before spring break, and then the rest of logarithms that we do after spring break. So the part of logarithms that you will be on the hook for section 3.2 is graphing and the properties. So the first one we're going to look at is this one, the one on graphing. This is number 94. This is just a one-page thing. And honestly, you don't need too much new information to be able to graph a logarithmic graph. In just about 3 minutes here, I can show you how to graph something like this without a calculator. So the reason why we did inverse functions before we jump to chapter 3 is to make this part a little bit easier. So hopefully this helps. But the first 3 questions, this is really what the only new piece to this, only new thing I haven't told you all year. The rest of this handout is about connecting these pieces together. So you need to know the relationship between these. 3 to the x and log base 3 to the x are inverses of each other. Also, log base 8 to the x and 8 to the x are inverses of each other. So we will ask you questions like what would be the inverse of 5 to the x, and you need to know that is log base 5 to the x. Or we might ask you what is the inverse of log base 2 to the x, and that would be 2 to the x. Until we're a little bit deeper into logarithms, I can't show you why it works that way, but you just need to notice this pattern. How that is supposed to help you is if I'm trying to graph this function in number 6 without a calculator, you probably just aren't experienced enough with logarithms to know what this graph's going to look like quickly. I could graph this guy very fast. I could go straight to this graph, but that's because I've done a few of these. What I would recommend for you to do is start off with the exponential function, like 2 to the x. That's what we just did in section 3.1. So you could do 2 to the 0, 2 to the first, 2 squared, 2 to the third, 2 to the negative 1. As many points as you'd like, but it's good to have a few very specific points, and that's exponential growth, so we know the shape of the graph. And then the big concept that you need to understand that's going to make graphing logarithms easy or difficult if you miss this is 2 to the x is inverses with log base 2 to the x. And inverse just means I'm switching x and y. So 0, 1 becomes 1, 0, 1, 2 becomes 2, 1, 2, 4 becomes 4, 2, 3, 8 becomes 8, 3. And that quickly, we have an idea of what the logarithmic graph looks like before transformations. Notice You don't have to know this for this one, but notice it has that line symmetry at y equals x. That makes them inverses. The last part would be just your standard transformation rules. If you add 3 to x, that's going to shift it left 3. So again, all of these points I was sure about, just shift them left 3 and replot them. Whoa. 1, 2, 3, 1, 2, 3. Reconnect them, and just like that, we have graphed log base 2 of x plus 3. So I'll do that again on the next graph, but I just shifted log base 2 of x left 3 because of the transformation. I got log base 2 of x by knowing it was the inverse of 2 to the x. And so I started with 2 to the x, took all of the points I was sure about, switched to x and y to get his inverse, and then shifted all of those points left 3 to get the graph they were actually looking for. You're used to the inverse stuff. You're used to the transformation stuff. You just kind of need to understand why I started with this. I started with 2 to the x because I saw I needed to do something with log base 2 to the x. Okay, now normally you're not going to have these leading questions. A lot of the times it's going to be like this. So if I was trying to graph this, and again this has quite a few transformations, but that just makes it a longer question, not a more difficult question. But within all this mess, its inverse would be 3 to the x, which I can graph quickly. I start with that because he is inverses with log base 3 to the x. So take every point we were sure about, switch x and y, replot them, and I already know what log base 3 to the x is. Notice the symmetry at y equals x. And then we can apply the transformations. This one just happens to have 3 different transformations. Looks like we need to go left 5, then we need to reflect over the x-axis because of this negative. So this would be negative log base 3 of x plus 5. And then finally, the minus 1, of course, goes down 1. So move all of the points I was sure about down 1, reconnect, and this is optional, but to me my graph gets a little bit too busy here. I've got too much going on, so those were good steps to help me see what I was doing, but I really don't need them in the long run. Usually I erase them as I go. So again, knowing what 3 to the x looks like should be a gimme for knowing what log base 3 to the x looks like, because you just switch x and y, they're inverses, and then you do all the transformations. So most of these wouldn't have this many transformations, but I shifted them all left 5, graphed it, flipped them all over the x-axis, regraphed it, and then shifted them all down 1 and regraphed it. Again, I'm not focused on the transformation rules very much because I know you guys have seen those for a long time. But of course, if you're not comfortable with those, you need to spend some time on that outside of class. And then we will ask you questions about the graph, but it's questions that you guys are used to seeing. So now that the graph is done, I can see the domain is -5 to infinity. The x-intercept, we'll talk about more specifically on one of the other handouts. This one's somewhere between -4 and -5. So by the end of the other handouts, you would have an idea of how to find that exactly. Don't assume it's -4.5. And a very common one is vertical asymptotes. All logarithmic graphs have vertical asymptotes. So this one had one at x equals 0, but then I shifted it left 5, which moved it to x equals -5. The vertical line that the graph can't cross. And it has to be x equals instead of y equals because it's a vertical line, not a horizontal line. So again, you should know the transformation rules. You should understand what it means to be inverses. You've got to understand how these pieces fit together. But really the only new information I'm giving you here is questions 1 through 3. Make sure you understand how those two relate so that you can pit them against each other to get the graphs that you need. And again, you'll have some graphing practice when we get to worksheet 1 and 2. I will go over the graphing one more time on worksheet 1 and have you try it on worksheet 2. What?
Well, how do you do the x-intercept?
You have to do it algebraically. You'd have to plug 0 in for y, and then you have to solve this. So we'll talk about how you would go through that process. It's just
now we just leave it blank.
Yeah, just leave it blank for right now. It's fine. You could at least say you at least see kind of where it is. I mean, you have an estimate of where it is. Yeah. Yes, and we'll have to do better than that, but for now it's fine. Okay, the next 2 pages you picked up make up 95, starting with this one. So again, the first part was focused on graphing. This one's going to focus on the properties. Now again, this can be very easy for some people. If you did, I know you did this in Algebra 2, or at least if you did Honors Algebra 2. And so if you remember it, it's not too bad. If you forgot it, then the stuff's important. You got to relearn it. So, but the piece of advice I will give you is that you need to know the properties to survive this section. And when we come back from spring break, 3.3 and 3.4 are still about logarithms, and you'll still be using the same properties. So, all right, the first thing is convincing you that you need to know, or why you need to know logarithms. So, if I ask you this question on the left, you should be able to answer this one. 2 to what power gives us 4? 2. Okay, but then over here, 2 to what power gives us 5?
Square root of 5 of 2. No. Never mind. Square root of 5.
Nope.
Log base 2 of 5.
Correct. But notice he said log. So this is why you need logarithms. Logarithms are the only algebra trick to ever solve for a variable in the exponent. Unless, if it's one that comes out to a nice whole number, sure, you don't have to do that. But this answer is going to be a little bit bigger than 2. And if you continue to pursue a career in math or science, you've got to be more accurate than to just say it's bigger than 2. So I'm going to come back to this one in just 1 second. Okay, I don't think it was y'all who told me this, but one of my pre-cal classes talked about on the ACT, I think this was one of the skills that they had tested you on, going from exponential form to logarithmic form and vice versa. So that is one thing we ask you to do as well. So all 4 of these are considered exponential form. So logarithmic form is going to have the word log in it. And to make these logarithmic form, you just have to do one thing. You have to switch 2 of these things around. You just have to know which 2 they are. So for this one, it would be the 2 and the 9. So logarithmic form would say log base 3 of 9 equals 2. This one, you would swap the b and the c. So logarithmic form would say log base a of c equals b. Switch to 2 and the 16. So this one says log base 4 of 16 equals 2. Or switch the x and the 5. Notice I'm switching the same 2 things every time. So log base 2 of 5 equals x. This, well, not only does this show up as a skill that they just ask you to do, we will do the same thing Your ACT apparently still asks that. But this is also a common and easy way to solve exponential equations. So let me go back up to this one. This is in exponential form. And notice if I switch it to logarithmic form, I think, is that what you said, Wesley?
Yeah.
Okay. If you switch it to exponential form, or I'm sorry, logarithmic form, put log out front, switch the x and the 5, there's your answer. That's what x equals. The exact answer is log base 2 of 5. Now, before we're done with this handout, I will have to tell you about something called change of base so that you can know how to type this in your calculator and get a decimal out of it. But for right now, I will just type it in and tell you that's about 2.3. So I knew it was a little bit bigger than 2, but of course in my calculator I have it to 9 decimal place accuracy. So now, if you can go from exponential form to logarithmic form, the next skill is just undoing that. Exponential form doesn't have the word log in it, but for you to remove log from your equation, you have to swap those two things back. So you're just undoing what I just said in the last little section. So 3 squared equals x, a to the b equals c, 8 to the x equals 11, 2 squared equals 4. If you can go one direction, you should be able to go the other direction also. Of course, I didn't see that last ACT test. Well, just the juniors. If you're not a junior, you probably don't know what I'm talking about. But the test that the juniors took, the ACT that they took on campus last week, was that last week? Okay, seems like 3 weeks ago, but I don't know which one it was. I don't know if it was this one or this one, but they're really the same thing. If you can go one direction, you should be able to go the other direction. Okay, some logarithms, in fact the ones you have on your calculator, if this doesn't convince you that logarithms are important, I don't know what will, but your calculator has 2 buttons specifically for logarithms. So the first one, log, notice it does not let you type in a base number here. It doesn't give you the option. And right below that, ln is actually for something called natural log. Same thing, it doesn't let you type in the base. It's similar to, in mathematics, when we talk about x, everybody knows we're talking about 1x. When there's no base listed, it's an understood base 10. Very good. So if it makes you feel better when there's not a base there, just squeeze a base 10 there so you can see it. Whereas natural logs, if natural logs bug you, you can change it to log base e. Very good. Log base e. That same number e that is in the compound interest formulas. And I can tell you, for those of you that do calculus, when we do logarithms in calculus, 99% of the time it's natural logs, not other logs. So again, these are the exact same thing. So if you feel more comfortable with it written this way, just take one extra step and write it that way. This is saying exactly the same thing as this. Putting a 10 here doesn't change the question at all. Putting a 10 here doesn't change the question at all. Feel free to make those changes or add the 10 in until you can do that mentally and you don't have to write it out. All right, a lot of time with logarithms, you should be able to do some of these in your head without a calculator. So I'm going to show you the long method and then the short method. So the long method, and again, this is without a calculator, so these won't be too messy. The long method would be set it equal to x. And so once you know what x equals, you know what the answer is. Well, the only type of logarithmic equation I've told you how to solve yet is by switching the forms. This is logarithmic form. You could switch it to exponential form, and just our brains handle exponential form a little bit better just because we're more familiar with that. So 7 to what power gives us 7? 1. Okay, let me do the long method one more time, and then I'll show you the little bit shortcut. Okay, no base written here, so this is an understood base 10. Set it equal to x. If it's in logarithmic form, try switching it to exponential form, and there's a good chance your brain's going to understand it better in exponential form. So 10 to what power gives us 100? So, 2? Good. Be careful not to say 10. It's easy to fall into the multiplication, but we're doing exponents. So you can do that if you want to, but that's really one more step than you really need to. What I would prefer you to do, and what most math people do, is when I look at this, just phrase it this way in your head. I'm going to knock basically all these questions out in about 30 seconds. This is saying 7 to what power gives you 7, which is why the answer is 1. This is saying 10 to what power gives you 100, which is why the answer was 2. This is saying 10 to what power gives you 10. This is saying 10 to what power gives you 1?
Minus
0. Anything to the 0 power is 1. This is saying 3 to what power gives you 27?
3.
Good. Don't say 9, say 3. Don't fall into the multiplication trap. If natural log bugs you, change it to log base e. This is just saying e to what power gives you e? 1. This is saying e to what power gives you 1? 0, because anything to the 0 power gives you 1. And this one's a little bit harder. You have to use exponent rules. So 2 to the first would be 2. 2 to the what would give me 1/2. Very good. Remember, a negative exponent in the numerator is the same thing as moving it to the denominator to make it a positive exponent. So that one's a little harder to do, but if you know your exponent properties, then you can do that one. So again, I can answer those very quickly. Of course, I could have answered them even quicker if I wasn't verbalizing it the whole time. But if you know how to read a logarithm, it's just asking you what exponent could you put on the base to get what you're taking the log of. And we wouldn't ask you ones that had some, insanely weird decimal, not something that you couldn't do in your head. Or if we did, you would have a calculator and you would have this thing called change of base formula. So if you remember at the start of the page, there was one I said I put in my calculator to round forest. The way I did this was with change of base. So I will, before we move on from this little section, bless you, show you, depending on what calculator you have, you can kind of get around change of base, but we still test you on it. We still insist you know it, because I think it still shows up on the ACT. I know there's one thing in calculus that you can understand better if you know change of base, and if you take college algebra at some point, that is something that they still teach and test. So you need to be familiar with change of base. But the idea of change of base is, if I want to round this answer, if I want to get this within like 3 decimal places, because 3 to what power gives me 7, I don't know. I can't do that in my head. I know it's between 1 and 2, because 3 to the first is only 3, and 3 squared is 9. And if I go to my calculator and hit the log button, it doesn't let me put a base of 3. So the change of base formula says that you can do base 10 if you do log base 10 of 7 over log base 10 of 3, or you could do natural log of 7 over natural log of 3. You need to know both of these because we usually ask this as multiple choice. So you can't just know one of them. So if I want to know log base 3 of 7, I could ask my calculator, what's the log of 7 over the log of 3? Or what's the natural log of 7 over the natural log of 3? Same thing. I knew it was between 1 and 2, but with change of base, I know within 8 or 9 decimal places, about 1.771. 1.771. So this guy for change of base, again, you should be able to estimate the answer. This answer should be a little bit bigger than what? 2.
It'll be
Big,
bigger than 2.
all right, because 5 squared would be 25, and that's almost 27. So in my calculator, I could do log of 27 over log of 5, or I could do natural log of 27 over natural log of 5. Just make sure you know both ways work. I'm going to type it in both ways on the screen just to help convince you. Again, we knew the answer was a little bit bigger than 2, but with change of base, we know it within 8 or 9 decimal places. About 2.048. 2.048. Okay, there's one catch, and I'm only going to talk about this for 30 seconds. You still need to know change of base. We still hold you to that on quizzes and tests because, again, I'm pretty sure they still refer to it on ACT. I know you need it for college algebra, and if you're doing calculus, there's one thing that you can understand why it works a little bit better if you know this. But technically, your calculator can do these without change of base, depending on your calculator. If you have a TI-84 and it's not an old one that you never updated the firmware on, the operating system, you can hit Alpha Window and you get this extra menu of stuff that they added to the calculators after the TI-83s. It's a convenient place to find absolute value sign. In calculus, we use 3 for derivatives and 4 for integration quite a bit. But option 5 says log base, and if you do that, it actually lets you type in the base that you want. So if I do this one, I can put the 3 where it looks like it's supposed to go and the 7 where it's supposed to look like it goes, and see how it gives you the same answer. So again, I don't keep talking about this because we still expect you to know change of base, but if you want to know that for the ACT, I don't think that's any quicker than just using change of base, but your calculator technically can do that. So if you want to write that down so that you know for the future, Alpha Window option 5 is one place you can access that. You don't have to know that for our class though. Okay, so hopefully I've convinced you why we need logarithms. I've shown you how to estimate logarithms in a calculator with change of base. We talked about how to evaluate logarithms in our head if the numbers are nice enough. And we've talked about switching forms. So now getting into some of the properties. This is probably the most important property. This property says if you have an exponent on something you're taking the log of, that exponent can come down out front. You need to know this property for this section. Eventually, I didn't mean to make duplicates here. Eventually, after spring break, you'll need to be able to do a question like this. But for your notes, I just want to show you an example and have you copy down an example why this is important, instead of just saying it works, memorize it, and be able to use it. But if you're trying to solve an exponential equation, so your variable stuck up here in the exponent, and again, you can put an X next to this so you remember you don't have to study it, but you still need to copy it down. In math, one of our special tricks is you can take the log of both sides, and that's considered to be mathematically legal because I do it to both sides. And the reason why you do that sometimes is because now the x plus 2 is an exponent on something I'm taking the log of. So the x plus 2 can come down out front. That's what this property says. And then if you really wanted to solve this, it still has a few more steps, but the hard part's over. Natural log of 4 is just a number, natural log of 6 is just a number. I could distribute this number. I could undo add with subtract. And I could undo multiply with divide. Again, it looks kind of scary, but you're just undoing your normal equation solving stuff. But you have to have that logarithm property to understand why the x is coming out of the exponent. Again, you don't have to be able to do a question this complicated until after spring break. I'm just showing you why this property is so useful algebraically. Okay, another property that you need to be aware of, and for our class you just need to be able to, well, you'll see what you need to be able to use it as. You need to recognize the pattern and be able to give out the answer, but I'm also going to show you an example of why we need this and why we need you to recognize it for later math classes. This is one of the easiest ones for sure. I can't tell you why it works yet, we haven't reviewed enough logarithm stuff, but I can show you before the test if you're interested. This property says if you have a number whose exponent is log and the base is the same number of something, this is just going to simplify to the something. So 3 to the log base 3 of 100 is just going to be 100. 71 to the log base 71 of 2 is going to be 2. You just need to recognize that pattern for this class. To show you why it's important, calculus students are actually using this right now in their current unit. They used it a lot more last week though. But in calculus, a lot of times, you need to go from natural log of y equals to just y equals. And a common thing that students think you can do is just divide both sides by natural log, but that doesn't make sense because it's not natural log times y. You're not undoing multiplication. It's natural log of y. They're stuck together. So again, I want you to copy down the notes, but you don't have to study this for your quiz. I'm giving you some insight of why it's important instead of just saying memorize it and do it. So we have this fancy algebra trick called exponentiating, which is where we make the entire left side and right side of the equation an exponent of something. So I would make both of these the exponent of e. And that seems kind of crazy at first, but what does this become?
Cancels out, right? Y.
Cancels out to what?
1.
Not 1.
Y.
To y. If this is e to the log base e of y, it just becomes y. So if you need to go from natural log of y equals to just y equals, you exponentiate both sides so that you can use this property and you can get it down to y equals. And of course, as usual, if you guys have any friends in calculus, run that by them and ask them if that's really important or not. And I think you'd be surprised how often we use that. But again, you don't have to do this for this class, but you do have to know this property. You'll see how we use it. Easy questions. Okay, we're getting pretty close to the end here. This is very similar to what we've talked about, except to even start these questions, you really want to start off with exponent rules. So when I look at this question, instead of having 10 to the 5th in the denominator, I would move it to the numerator. Instead of having e to the 7th in the denominator, I would move it up to the denominator, up to the numerator. The reason why I think to do that first step is because now I can fall back on the other stuff we've talked about today. -5 is an exponent on something I'm taking the log of, so I'm free to bring that down if I'd like to. What is the log of 10? 1, because this is asking 10 to what power gives you 10. So in the end, your answer just came from -5 times 1. But if you don't think to rewrite that fraction the way I did, then there's not much else you can do. This one, now this is an exponent on something I'm taking the log of, so I can freely bring that down out front. What's the natural log of e? 1. This is saying e to what power gives you e. So your answer comes from negative 7 times 1. Now, if you have more than one term and you bring it up, make sure you make all the terms negative. It's not just the x that would become negative, it's also the negative 1 that becomes negative. But then you can bring that down because it's an exponent on something I'm taking the log of. The log of 10 is still 1. And so that would be your answer. Move this to the other side of the fraction. Make sure that it's not just the 3x that becomes negative, but also the 2. Now that stuff is an exponent on something we're taking the log of, so it can come down out front. Natural log of e is 1. E to what power gives you e? That's one that you're going to hear a million times, so you really want to just memorize that one. And of course, notice I had x in my question, so I have x in my answer. These aren't equations. We're not trying to solve them. We're not trying to solve them for x equals. You can have x in your answer. We're just simplifying. Okay, so sometimes, especially if you're taking the log of a fraction, you might think to rewrite it this way. Okay, we need to talk about extraneous solutions and how to find vertical asymptotes. So, the same way I talked about, just going to do a quick little sketch of these 4. The same way I talked about with exponential functions, how 2 to the x and 3 to the x and 5 to the x and e to the x and 10 to the x all look the same. Therefore, their inverses would basically look the same. Log base 3 to the x, log base 5 to the x, log base e to the x, log base 10 to the x. They're not the exact same graph. They do rise a little bit faster or slower. They do hug the y-axis a little bit quicker or slower. But if you don't have any transformations, logarithmic graphs basically look the same. They have the same domain, the same range, the same x-intercept, no y-intercept, etc., etc. So if there's no vertical asymptotes, using this graph as an example, your vertical asymptote will be at x equals 0. That's where the vertical spike in the graph would be. If you shift the graph left 4, everything goes left 4. The domain goes left 4, so does the vertical asymptote. Would be at x equals 0, so if the whole graph shifted left 4, the vertical asymptote's moving left 4 also. Okay, and then these two, I don't know if you guys have seen this before in Algebra 2. There's a good chance that you didn't. But let me talk about, you don't have to write these graphs down, but I just want to give you a visual. This would be the parent function. If I put a negative next to x, what transformation is that? Good. Y-axis, good. Not the x-axis. X-axis would have a negative out here. Notice that doesn't change where the vertical asymptote is. It's still x equals 0. Here's the part that I'm concerned about and why I have it on your notes. Because again, I don't know that you saw this much in Algebra 2, if you saw it at all. When we add 4 to x, you're used to that meaning what?
Left 4.
Right, and so most of the time it is left 4. But if you're reflecting over the y-axis, those rules actually are switched. Because what's happening is, it doesn't look like it, but the negative doesn't just go to the x, it actually goes to the 4 also. So even though this looks like it should be left 4, because you're reflecting over the y-axis and this negative is really going to both of those, this is actually going right 4, which would move the vertical asymptote right 4 also. And you feel free to graph that in your calculator if you need to see a visual to be convinced. So to say the same thing again, if this was just natural log of x, I know what the graph looks like. Vertical asymptote, x equals 0. If I reflect it over the x-axis, or I'm sorry, y-axis, the graph looks completely different, but it's still going to have a vertical asymptote at x equals 0. But if you reflect over the x-axis and add 7 to x, it's really like you've got a negative x minus 7. So it's really going right 7, which would move your vertical asymptote right 7 too, to x equals 7. So again, it's not a real common thing, but anytime you reflect over the y-axis, the rules for horizontal transformation switch. What usually goes left now becomes right, and what becomes right goes left. So. Okay, and then finally, we do have you solve a couple of equations in this section, but they're very basic ones. In section 3.3, when we come back from spring break, we'll talk about expanding and condensing logarithms, which I think you've seen before. And in section 3.4, we solve more complicated equations, but we give real basic ones in this section. Yeah, John.
Oh, how do you know to do the reflection before you move it right?
Just order of operations. If I plug the number, like if I was making a table and I plug a number in for x, the first thing you would do is multiply. So that's how I know to do that transformation first. And then the next thing I would do is add. So that would be your next transformation. Yeah.
This goes back a little bit. When you plug log in your calculator, is it a number or how does that work? Like,
Log of what?
that's
Log by itself doesn't mean anything. It has to be log of what?
Like dividing a number or x. Okay.
This has a base of 10. So whatever I put here, I would be asking my calculator, what exponent on 10 gives me this number? So if it's 10, it's going to say 1. If it's 100, it's going to say 2.
Okay.
Because we're working with exponent stuff. Okay, so last part, give you an example of some of these questions. Again, these work out really nicely, but we have to be careful not to take extraneous solutions. And so an extraneous solution is going to occur, and you need to add this to your notes. Never take the log of 0 or any negative number. Now, you've already seen this as a visual earlier today. I just didn't verbalize it this way. If I graph a log graph of any base, they all basically look like this. Notice how it doesn't exist at 0, because it doesn't make sense. There's no exponent on anything that gives you 0. And he doesn't exist for the negative numbers. There's no exponent on 10 that's going to give you a negative number. It doesn't exist in the graph because we can't do that. So if I ask you to solve this equation, it might look kind of messy, but notice this side's log base 3 and this side's log base 3. So that stuff's already equal. We just need to make sure that what we're taking the log of is also equal. So you could just set the insides equal to each other and then solve your algebra equation. Now, you might think that this is an answer you can't keep, but that's not what I said. I didn't say your answer can't be negative. I said you can't take the log of a negative or 0. So what you would need to do before you circled this answer is you'd want to go plug it into the original problem. You would get log base 3 of 3 on the left and log base 3 of 3 on the right. So first off, that should make you feel good that the left and the right are the same. And second off, I can take the log of a positive number. So this is perfectly fine. Log of 3 makes sense. Positive numbers exist on logarithms. But if I do this example, this is log base 3, this is log base 3, so that part's already equal. I just need to make sure that the parts I'm taking the log of are also equal. And so a quadratic, make sure you put everything on one side set equal to 0. It's probably going to factor. You get 2 answers. And if you don't know that some of these could be extraneous, you're going to think both of those are your answer. But really only one of these 2 is our answer. You should want to plug these in and see what you get. So if I plug in 1 into the original problem, I get log base 3 of -2 equals log base 3 of -2. That sounds great. The left and the right are equal, but this doesn't make sense. There's no exponent on 3 that's going to give you -2. This is what we call extraneous. It's not that I did anything wrong. I factored right. I solved my quadratic right. My first step is okay. Logically, it's okay. But when I just pretend like the logs aren't there, I'm pretending like there's no restrictions. Whereas if I plug in -3 to the original problem, I get log base 3 of 6 equals log base 3 of 6. Left and the right are equal, good sign, and I'm taking the log of a positive number. There's only one answer there. The other one is extraneous. You should want to plug them into the original problems to check, but if you're taking the log of 0 or the log of negative, that doesn't make sense, and you need to not include it as one of your final answers. Okay, so a lot of information, but now we're going to kind of reset here. Your last handout, the front is 96, and so I'm still with you here. I'm still going to give you a little bit more guidance, but the front is 96 and the back is 97. These two are the ones that look most like your quiz. And I'm going to do 96 for you or with you. We can kind of discuss it as a class so I know what to emphasize more. And then you need to practice 97 on the back on your own to see what you actually need to review and whatnot. Okay. So the first 12, well, there's like 3 sections here. 1 through 12 are just asking us to simplify with properties. Then the next 6 ask us to solve some basic equations. And then the last set will ask us to try to do some graphing. So even though there's 12 questions at the top here, there's not 12 different things going on. Some of these properties are being repeated. So let me explain question 1 to you, and then I will ask you to try to find some others within 1 through 12 that you think work out the same way. So when I look at question 1, I see 7 is an exponent on something that I'm taking the log of, so the 7 can come down out front. Occasionally you actually move it up the other direction, but for us we're going to just be moving it down for now. What is log base 2 of 2? 1, because that's asking you 2 to what power gives you 2. So your answer just comes from 7 times 1. Okay, look at the rest of 1 through 12. What's another question that you think would work out the same way, same property?
4.
Not quite 4. What else?
11.
Okay, I agree, 11. Notice 5 is an exponent on something we're taking the log of, so the 5 can come down out front. Log base 4 would be 1. 5 times 1 is 5. I see one more that works out exactly the same way. Nope, not 2. 2 is a different property.
3.
It is 3. X is an exponent on something I'm taking the log of, so X can come down out front. If the natural log still doesn't feel comfortable to you, remember you can change that to base E. So this is just asking you e to what power gives you e. So your answer comes from x times 1, or x. Again, we're just simplifying. We're not solving an equation. I don't need to get x equals something. My answer can have x's in it. So all 3 of those are the same thing. Okay, now question 2 is a different property. So let me explain that one, and then I'll ask you to try to identify where it's being used in other questions. This is the property that says if you have a number and his exponent is log, the base is the same number of something, it's just going to simplify to the something. 3 to the log base 3 of 8, it's just going to simplify to be 8. For your sake, it's just pattern recognition on those. Okay, what else 1 through 12 works out the same way? You say 12? I agree. 10 to the log base 10 of 7 is just going to be 7. And 6, very good. E to the log base E of 5 is just going to be 5. They're not difficult, they just, you either know that property or you don't. There's not much else you can do. Okay, I would say 4, 5, 8, and 9. I'd say all of these are on the easier side. These are ones, if you know how to read a logarithm, you don't even really need any properties. So, natural log of e is just 1. E to the first gives you e, so this is like 5 times 1. Same idea over here. This is negative 2 times 1. And then 5 and 8 are basically the same thing. Excuse me. This is saying e to what power gives you 1, and this is saying 10 to what power gives you 1. But anything to what power gives you 1?
0.
So really the same idea. Oh, and 10, I guess. This is saying no base here. If it makes you feel better, put in the 10. This is just saying 10 to what power gives you 10. So that would be 1. And the hardest of these, one that you'd probably want to look at for a minute, but again, I give you half of next class to do that, which will be 50 minutes. This is a long time. But this is like near that last page in the notes that we did 4 of these. If you're trying to do the log of a fraction, you might want to rewrite it. So instead of e to the positive 2 in the denominator, make it e to the negative 2 in the numerator. And if you do that, now it's like question 1, 3, and 11. Negative 2 is an exponent on something I'm taking the log of. You can bring it down out front. For the 20th time today, natural log of e is 1, so your answer comes from negative 2 times 1. So 12 questions, but really there's, if you can read a logarithm, there's about 3 or 4 different things you need to be looking for in those. So worksheet 2 will be similar. Same properties, same approaches. So in just a few minutes, I can have you try those. Okay, the next section, let's look at the solving equations. And again, these will be really basic in this one. There's only one of them that requires a little bit more thought, and that's number 17. But number 13, I can simply just simplify this like we did above. What is log base 6 of 6? Okay, and if you know that, you're just left with an algebra 1 equation. Okay, same idea on number 14. 7 to the log base 7 of 8 would be 8. And then, at least this is something you can do in your head. The answer is not 4, don't do multiplication. 2 to the third gives you 8. 2 times itself 3 times gives you 8. So, same thing we did above, but then you just do one more step to solve. Like your notes, if this side is natural log and this side is natural log, that stuff's already balanced, so you just need to make sure that what you're taking the natural log of is the same. So you can set those equal to each other and solve. Just be careful that that answer is not extraneous. When I plug this in, I get the natural log of 18. Over here I get the natural log of 18. Nothing's wrong with that. I can take the log of 18. I can't take the log of 0. I can't take the log of a negative. Same idea on number 16. Log base 2 is already equal to log base 2. So I would just need to make sure that 3x equals a half. Divide both sides by 3. Okay, let's come back to 18 or 17 because it's going to have a couple steps. But number 18, what would x have to be for this? 3. If x is 3, then you have log of 6 on the left and log of 6 on the right. Again, real basic ones in this section. Okay, the one that you probably want to look at again, and I'll just be honest, I don't even remember if there's one like this on the quiz or not, but this is one that we can do in our head, but the answer is not a nice whole number. It's not so messy that we can't do it, but it's messy enough that we need to slow down and do it in a couple steps here. So first off, I know the answers between 1 and 2 because 8 to the first is only 8. Not quite 16, and 8 squared is 64, way bigger than 16. So if I know the answers between 1 and 2, that tells me my answer's got to be a fraction. So I ultimately want to know 8 to what power gives me 16, and I know this is a fraction. Well, that's kind of hard to do. But if we do it in 2 steps, it's a lot easier. Because I can raise 8 to the 1/3. Raising to the 1/3 is the same as doing cube root. I didn't do 1/2 because the square root of 8 doesn't come out to a nice whole number. The cube root of 8 does come out to a nice whole number. So I do that first. It lowers the base, and now this is easier for me to see. 2 to what power gives me 16?
4.
Okay, so I want to raise it to a 1/3, and I want to raise it to the 4th. So to do those at the same time, I want to raise it to the 4/3, which is between 1 and 2. So again, I would recommend raising it to a 1/2. If it square roots nicely, raise it to a 1/3. If it cube roots nicely, raise it to a 4th. If it 4th roots nicely, get that base to be lower, and then the second half is a little easier to see. But that's a good one to look back at. Okay, and then finally on to the part that we started with, which was the graphing. So the first question is trying to lead you into the right direction. You should be ready to state that the inverse of 2 to the x is log base 2 to the x. The reason why we want you to know that is if you know what 2 to the x looks like, which you should from the last section, you could take those points, switch x and y, and you would have his inverse, which is log base 2 to the x. Notice the line of symmetry at y equals x, which makes them inverse functions. And then you can worry about what you actually have to work with. Same exact graph, log base 2 to the x, but this one needs to go left 4 because of the transformation. So here is what they were trying to get me to find, f of x. In fact, personally, I would erase the other stuff just to get it out of the way. But 2 to the x is just a tool to help you get log base 2 to the x. And log base 2 to the x is just a tool to help you get log base 2 of x plus 4. Then once I have that graph in front of me, I can see the domain. It's -4 to infinity. I can see the range goes down and up forever. It does go up slowly to the right, but it does keep going up. So the range hits all the y values eventually. I can see the vertical asymptote at x equals -4. I can see the x-intercept, except I got to write it correctly. That was one of the points I kept up with, so I'm sure that's hitting exactly at -3. It's not just an estimate. I can see the y-intercept, same thing. And I can even see the 0.43. But let's say that I was not sure about these two. They look like they go through 0, 2. They look like they go for 4, 3. But again, my graph is not perfect. You can check these very easily algebraically. Just take the equation, and if you want to know the y-intercept, you want to know when x is 2. When x is 2. when x is 0. So you could plug 0 in for x, and you could solve for y. What is log base 2 of 4? Which is what it looks like on the graph. And you could even check by plugging in 4 into the equation, 4 for x, and solve for y. 2 to what power gives me 8? 3. Just like the graph looked. So if you didn't feel super confident about those, just plug in 0 for x, solve for y. Plug in 4 for x, solve for y. Since those are nice whole numbers, that means that evaluating them in your head should also work out nicely. Okay, so you need to do the same thing for worksheet 2. Try to do it as a practice quiz if you can, please. So questions 1 through 12 are similar to 1 through 12 here. Then the next 6 are similar equations to solve, like here. And then the bottom is similar graphing, like the bottom of this. Okay. I apologize. I guess you guys took a little bit longer on the quiz than the other class because we've only got about 3 minutes. So between now, sooner is better than later because all this stuff is fresh in your head right now. But between now and next Tuesday, finish worksheet 2 on the back, check your answers. If you have specific questions, you'll have 50 minutes to study and ask those questions on Tuesday before we have to take this quiz and move on. So.